Yeah. First, we will talk about hydrometry. So hydrometry is the monitoring of the components of hydrological cycle, including rainfall, groundwater characteristic, as well as water quality and flow characteristic in the surface water. And this hydrometry can also be called the science of measuring water. So in hydrology, usually the problem lies in the measuring the discharge of the river or channel, which is mostly can cause the flood. It's usually from the discharge of the river or channel, or the discharge of the rainwater. There are many ways to measure river flow discharge, but in principle, what is measured is the cross-sectional area of river flow and the flow velocity at the measuring point. So the the thing that can be measured is not the discharge directly, but you have to measure the cross-sectional area of the river and the flow velocity at the measuring point, because Q equal to V times A. So the discharge equal to the flow velocity times the cross-sectional area. For the discharge measurement, there are 3 ways that can be done. These 3 different ways is the first one is the using formulation. So for the discharge measurement, you can use this formulation, Easy, Manning, and Stricker. But this 3 formulation is not for the discharge measurement, but it's for the flow velocity. So for the flow velocity, you can calculate it using Easy, Manning, or Stricker equation. The second way is using the measuring structures. And the third way is by direct measurement. For the discharge measurement formula, there are 3 different formula in calculating the flow velocity. For the Chezy formula, you need to have the Chezy coefficient here as 3, and then R is the radius hydraulic, and I is the inclination of the channel, like the difference elevation between the upstream and the downstream of the channel. And for the Manning, you need the Manning coefficient here as an N, and it's the Manning coefficient, and the radius hydraulic R, and the inclination of the channel I. And for the Strickler formulation, you need the Strickler coefficient as an K here, and then radius hydraulic and the inclination of the channel. So it depends on the coefficient that you use. You can use different equation or different formulation for calculating flow velocity, and then you can have the discharge measurement by multiplying the flow velocity with the area of the cross section of the channel. And the second way, using the measurement structures, there are 3 main types of measurement structures. I bet you already familiar with these types because you already did the laboratory practicum of mechanical fluids, fluid mechanics, and hydraulics. So the broad-crested weir and sharp-crested weir, and also flumes, these 3 you already did it in the fluid mechanics and hydrological experiment. Here, for example, in the field, the broad-crested weir is shaped like this, and then it is similar with the one that we have in the laboratory. Here is the sketch of the broad-crested weir. This is the weir. So from this structure, you can calculate the discharge based on the height of the water in the weir. And this one is the movable weir. The previous one is the non-movable weir. This one is the movable weir, the Romange movable weir. The function is the same to calculate the flow discharge. This is an example of the weir in the upstream view. Here we have the scale, so we can calculate the height of the water after the weir. And usually in the weir we also have scale, so we can calculate the water level before and after the weir. This is the sharp crested weir. So from the previous one is the broad crested weir. This is the sharp crested weir. So it the shape is similar, but this one is thinner than the first one. So this is the rectangular sharp crested weir, or you can also say that it is thin plate weir because of the thin structure of the weir. While for the broad crested weir, it has more bigger size of the weir. This is the Chipoleti that you see in the laboratory in the experiment, Chipoleti weir. And this is the enlarged view of the crest and side of rectangular sharp crested weir. So this is the zoom in size of the sharp crested weir, rectangular shape. The other shape that we have is the triangular, or here we can say that it is V-notch because of the shape is similar with the V. And here you see in the experiment, this V-notch sharp crested weir is the Thomson experiment. So yeah, for the V-notch, there are different degree of the angle. So the biggest one is the 90 degrees V-notch, and the smallest one is the a quarter of 90 degree V-notch. So around 28 degree of angle. This is the Chipoleti weir. So the shape is not so triangular, but not also V-notch. It is trapezoidal type of the weir. Here we have the comparison of 4 with 1 in the vertical and horizontal direction. And the last one, we have flumes. As you already know, like the shape of the flumes, the water is flowing from upstream to downstream. And from the channel, when you arriving in the flumes, there is this throat section, which is smaller than your channel. So here we can calculate the water level, and by the water level, we can also know the discharge of the flow using the equation regarding the flumes. So for the different structure measurement, we have different equation, as you already know. You already did it in the experiment of the hydraulics, of the mechanical fluids and hydraulics. So I don't need to explain it again because it's already done. And the third one is using the direct discharge measurement. So for the first one, you use the, what is the first one? Using the formula. And then the second one, you use the measurement structures. And then the third one, you use the direct measurement. For the direct discharge measurement, the discharge cannot be measured directly, but instead we measure the flow velocity and the area of river cross-section. For the direct discharge measurement at the measurement point, an observation of the water level can always change, and the place of the measurement point is called the hydrometry station. So for the water level measurement, there are two types of the measurement. First one is the manual, and the second one is the automatic measurement. The cross-sectional area of the river can be known if the shape or the size of the river cross-section at a measurement point is known, and the water level is also known. So besides calculating the cross-sectional area, we need to also calculate the water level in those river sections. By using the manual or automatic measurement. For the manual measurement, the measurement is done with the prediction stick, which is called pale shell. And this pale shell is used in certain times interval, for example, in 3 hours, 6 hours, and 12 hours. Here, an example of the calculation or the measurement of the water level in 6 hours, 9 hours, 12 hours, 15 hours, and 18 hours. So the interval is 3 hours. As you can see, the water level is not constant. Like it has different water level in each time intervals. So the shorter the interval, the better the data, but the more expensive it is because this measurement using the stick or the pale shell is carried out in directly in the field. So the method can be different. Like you can use the stick straightly here, and then you can also use it a little bit tilting on the side, and you can also use it with the certain level of water level, because on each cross section usually the water level is different, so you can calculate or measure the water level differently in the each level of the cross section of the river. And the second one is the automatic water level measurement. For this automatic water level measurement, you will need the device installed in the hydrometry station. The good thing is it will automatically record any changes in water level. So you don't need to manually measure on each, like for example, on every 3 hours you measure the water level in the river. No, you don't need to do that. For this automatic water level, you only need to install the device in the hydrometry station, and then it will automatically record any changes in water level over the time, and it will also automatically throw in the graph paper, which can be changed every once a week or once every 2 weeks. So the The water level can be seen in the graph. Either it is increasing or decreasing. You can directly see as the result of the automatic water level measurement. And to compare the automatic and the manual water level measurement, for the measurement with the automatic AWLR, automatic water level measurement, is more accurate than the measurement with fail shall sticks. And this is the graph which is provide the overview of the measurement result. As you can see here, for the AWLR, because it is automatic, it can present more accurate data than the fail shall. Because for the fail shall, usually there are time intervals. So it depends on the time that you carry out the measurement. For example, here for the time duration of T1 and T2, and then there is also T3, T4, T5 until T6, and so on. For the fail shall, it will not record the measurement results accurately because, for example, you need to calculate or measure each time step. But for AWLR, you can get the water level measurement on each time steps automatically. It can be seen then that the time between the two measurement interval, it's not the same. There are maximum and minimum values which are not recorded in the fail shall, but are recorded in the AWLR. For example, here we have the maximum values, but when we are using fail shall, for example, when these maximum values occur, it's not when the time we carry out the measurement. For example, we only carry out the measurement for the fail shall in this time step T1, T2, T3. But for the AWLR, this measurement is carried out continuously without caring about the time steps. So it doesn't depend on the time steps, but it depends on as long as the device installed, it can provide the measurement results. And for the flow velocity measurement, before is this previous one is the water level measurement. Next, we move to the flow velocity measurement. The measurement of flow velocity in the rivers can be done using these three things. First one is the buoy, and second one is the current meter, and third one is using dilution. I bet you already familiar with the second one, the current meter, because you already did it in the experiment of the fluid mechanics and hydrology. Fluid mechanics and hydraulics. When you are using buoy here, you have to select the straight river section and determine three locations of the river cross-section profile. For example, here we have a river, and then here we have the buoy. Buoy is the pelampung. Here we have the buoy, and then we determine the three locations of the river cross-section point. Here we have A, B, and C, the three locations. And then the floating velocity is the surface flow velocity in the river. So to get an average flow, you need to correct this flow velocity measured by the buoy. For example, here we have the flow velocity of L is the distance, T is the duration, and then here we have Vp. But to get the average flow velocity, you need to correct it with the correction K. So the velocity become K times the surface flow velocity in the river. Because as you already know, the velocity of the flow velocity will be different on each depth. But here for flow velocity measurement using buoy, we only calculate or we only measure the surface flow velocity. So to get the average flow velocity, it needs to be corrected. If the average flow velocity at section A is obtained and the cross-sectional area of the flow is known, then the flow rate at section A can be calculated as K equal to velocity times the sectional area. So the average velocity on each section will be different, and then you can calculate the average velocity for each section. And the next one is using current method. For the calculation using current method, there are two types of current method. The first one is the odd type, which has the horizontal axis of the this thing right here, the propeller. And then the second type is the price type with vertical axis of the propeller. So here in the picture is the horizontal axis. So for the vertical axis, it will be following the y-axis, and for the horizontal axis is following the x-axis. The measurement with the current method is done by first dividing the cross-sectional profile of the river into several parts that have the same surface width. This one, you already did it in the hydraulics experiment. But as I remember, you did it by dividing it into 3 different sections. But here the example is using 6 different sections. By dividing it into sections, you will need to measure the flow velocity on each section, and then you can use the data for calculation of the flow velocity. For example, if you only measure one time, you need to measure in the depth of measurement of 0.6 of the depth. But if you measure 2 times, you need to measure in the depth of 0.2 and 0.8 of the depth. But if you measure 3 times, which is the measurement that you've done in the experiment of the hydraulics, fluid mechanics and hydraulics, you need to measure in the depth of 0.2, 0.6, and 0.8 of the depth. But if you measure 5 times, you need to measure the surface 0.2, 0.6, 0.8, and the base of the section of each section. So here we have 6 sections. So if you measure 5 times on each section, so you need 30 times measurement to get the flow velocity on that area of the river. The flow velocity is obtained by the formulation contained in the current method tool. So it depends on tool. As you are, if you remember, you get the formulation and your formulation has like the tool constant. the A and the B, there are particular number of the constant which is need to be known, and it depends on the tool. It depends on the type of the current matter, and it usually has this information on each tool or on each current matter. And then for calculating the flow velocity, V equal to A times N plus B, where N is the number of the turns in the interval T divided by the length of the time of one measurement. So this is the number of turns of the propeller. It's a number that's shown on the device, and then you have to divide it with the length of the time of one measurement. For example, you measure it for 15 seconds, and then there are like 30 intervals, 30 numbers of turns, and then you will get the N is equal to 30 divided by 15 seconds. So it will be 2 turns per second. And then after that, you can get the flow velocity on each section. So the equation will also be different, depends on the how many measurements that you carry out in each cross section. For example, one measurement, you only need to calculate the flow velocity of the depth of 0.6. For the 2 measurements, you need to divide it with 2. 3 measurements, divided it with 3. And then 4 measurements, divided it with 4. And then and so on until 10 measurements, you need to divide it with 10. So if the velocity and the water level on each section has been obtained, the discharge can be calculated, because discharge is equal to V times A. So here we got the V, and then we can multiply it with the area of the cross section to get the discharge of the flow. There's also other method for the discharge calculation. There is this mid-section method and mean section method, and it calculates the discharge on each section. And by here we got the sum of the discharge on each section equal to sum of the velocity times the width of the section, and then times the height of the water level. So for each section, it will have different discharge, like for section A, B, C, D, E, and then for the river discharge, the section discharge will be accumulated. For the mean section method, because of the name, it's the mean. So we need to calculate the average of the flow velocity, and then times the average of the flow area, and then because of the discharge is equals area times velocity, so the section discharge will be the average of the velocity times the average of the area of the section. And for the discharge of this river can be obtained by accumulating the section discharge. And after we calculate the discharge, we already obtained the discharge. there is this rating curve. The rating curve shows the relationship between the water level in the river and the discharge. So previously we need water level to calculate the discharge, and by using this rating curve we can show the relationship between the water level in the river and the discharge by using the graph or the curve called rating curve. Usually rating curve consists of the x-axis of the water level and then y-axis of the discharge. So here we have the data of water level and discharge on time step of 6 and 9 hours. And for example, in 6 time step or in 6 hours, the water level is 1.85 and discharge is 43.2. But in the 9 time step or the 9 hours, the water level is decreasing, so that the discharge will also be decreasing. From these two data curves, this one, for the same t, the rating curve can be drawn. Like here, here we got the rating curve of K and H. So rating curve is always K versus H or H versus K. And we can see the connection between time steps and the water level, time steps and the discharge. And then after we see the correlation between time steps and water level and time step and the discharge, we can see the connection between discharge and the water level, which is shown in the graph. So usually rating curve is shaped like this, like because of the relationship between K and H is usually the same. Like if you have bigger H, so you will have bigger Q also. So the rating curve will be like this. To make a rating curve can be done by calculating the regression equation for the H and K data pairs. For example, here we have the K and H data, which is not so smooth. Like you see the red dots here. Actually, we cannot make a rating curve by only connecting these dots. No, it's no, because the rating curve should be like this, smooth like this. So we need to calculate the regression equation for the H and the K data pairs. It will be done easily using Excel. So Excel can be deliver the regression equation directly if you have like such a data. Like here you have the K and H data on each time steps, and by using the regression equation you can draw the rating curve. So here, for example, the possibility of rating curve shapes. For example, here, when the key is 0, of course, there is no water level, so there is water level of 0. But there is also condition where the water level is not 0, but the discharge is 0. So the rating curve will be like the second one. There's also a condition where the water level is 0, but the discharge is not 0. So that the rating curve will be like the third one. Regarding the rating curve, it is strongly connected with the types of the river. So different types of river can have different rating curve because it depends on the types of the river and the amount of the water flowing into the river. But based on the hydrograph, rivers are grouped into 3 groups. View from the continuity of their flow. The first group of the river is the ephemeral river. So for the ephemeral river, these types of the river will be discussed more deeply in the river engineering class. But here we can see the differences between types of the river and its hydrograph. So for the hydrograph, it is between discharge and time step. But for the rating curve, it is between discharge and the water level. So I hope you are not confused between the hydrograph and rating curve because actually it's two different things. Hydrograph is between Q and T, but the rating curve is between Q and H. For the ephemeral river, this is the river that flows only when it rains, because the groundwater level is always under the river bed. For example, here we have the river cross section. It has the groundwater level below the riverbed. Here we have the groundwater level. When it rains, of course, there is this surface runoff, the water coming in to the river. So the river, there are water flowing in the river. But if there's no rain, there is no water in this river because the water level is below the riverbed. The second type is the intermittent rivers. These intermittent rivers flows during the rainy season and doesn't flow during the dry season because of the groundwater level will be below the riverbed in the dry season. So the groundwater level is changing between the dry season and the rainy season. Here we have the blue one is the rainy season and the red one is the dry season. As you can see, when it rains, there's water flowing in the river, but when it's not raining, there's no water in the river. The differences between intermittent and ephemeral only flows when it rains. When it doesn't rain, even it is in the rainy season, there's no flow here. It is because, probably because of the types of soil, so that it cannot prevent the water from coming into the groundwater, so that the river becoming dry as soon as there is no rain. But for the intermittent rivers, even though there is no rain, as long as it's in the rainy season, the river can saving the water inside the rivers during the rainy season. But during the dry season, because the groundwater level will be below the riverbed, it's the same with the previous one, with the ephemeral. So there's no water flowing in this river. The hydrograph looking like this. Like for the rainy season, the hydrograph is quite big, but for the dry season, hydrograph is quite small. The third one is the perennial river. This is the river that always flows throughout the year. It doesn't matter if it's rainy season or dry season, the water always flowing in the river. The differences only in the water level. Because in the rainy season, the water level should be higher than dry season. So in the dry season, there's still there's still water flowing in the river, but the discharge is small. But in the rainy season, the discharge is quite big, so that the water level become higher. So for the perennial river, the hydrograph is looking like this. There's no zero in discharge because it always has discharge. Even though it's small, still have discharge. It's different with these ephemeral rivers. Sometimes there's zero discharge, which means there's no river flow. There is no water flowing in the river. And in the rainy season, the discharge is quite big. And then when the rain stops, the discharge is going back to zero. So now we begin to talk about the surface runoff itself. For the surface runoff, as you already see this graph between discharge and recharge, and E is the precipitation, I is the precipitation, P is the time. So if there is rainfall, part of the rainfall is discharging, become surface runoff, and part of the rainfall is recharging the groundwater, become the groundwater, so it doesn't flow above the ground. So for the hydrograph of the rainy season and the hydrograph near the end of the rainy season is different. As you can see here, the hydrograph of the rainy season has quite big discharge, but the near the end of the rainy season, beginning of the dry season, if there's no rain more, the hydrograph will be decreasing continuously until it becomes very, very, very small. And the hydrograph that we will talk about in this class is the single peak hydrograph, which means there is only one maximum discharge on this hydrograph. So for example, here we have the direct runoff. So the direct runoff is the water which is become the surface runoff. And then there's also base flow. Base flow is the water which is flowing without rain. So even though there's no rain, this is the minimum water level or the minimum discharge which is flowing in that river. There's also these differences between direct runoff and base flow. So this hydrograph drawn after one rainfall. As you can see, when the time is zero, the hydrograph is not started at zero because it has base flow. So for the type of the river that we talked about earlier, there is a river that has no base flow, which means if there's no rain, there's no flow. But here we have the example of hydrograph, which has the base flow of a particular amount of base flow here. so that the hydrograph is not started at 0, but it started at the amount of the base flow. And then after that, it increased continuously until it reached the maximum discharge. And then after peaking in the maximum discharge, it decreased continuously. So for this single peak hydrograph, there are some of the properties of the single peak hydrograph. Here we have the ascending curve. So when the hydrograph keep moving increasingly, and then we got the peak curve. Peak curve is the D, B, and C. And after that, we got this falling curve. Usually falling curves happen when the rainfall stops. And then we got this peak discharge of B, and C is the turning point or inflection point. E is the end of direct flow, which means it's starting to become base flow again. PC is the concentration time. So the concentration time is time that river needs for the water flowing from the upstream to reach downstream. And there is this flow-based time or time-based. It's actually the time from the rainfall until the water flowing until it comes like before rainfall. So the time base is the time total since the beginning of the rain until the water stops flowing. There is this base flow. If there is no rain, the flow in the river is called base flow, which is the supply of groundwater to the river. So the base flow discharge equation, if there's no data of the base flow, we can calculate the base flow using this equation, like Q equals to Q0 times E times E power minus alpha times T, where the current discharge, the discharge that we need to calculate, equal to the initial discharge times Euler's number times power of the coefficient times the time. For example, here we have the data of in a watershed. There is this period without rain. After 10 days without rain, surface runoff will be 100. While after 40 days without rain, the surface runoff will be 50 meter cube per second. What is the equation of the depletion curve? And how is the flow rate after 120 days of no rain? So because the old flow area is without rain, the flow rate is the base flow rate. So the depletion curve equation, we can use this equation that we already saw before for the base flow. Because of this period of without rain, of course, the discharge is from the base flow because there's no rain. So for this curve, we can use this equation, And we know that Q0, our Q0 is 100 meter cube per second. This is the initial data after 10 days. And then we got the Q of 50 meter cube per second after 40 days. So between Q and Q0, which one is the first one? The first one will become the Q0, and then the second one will become the Q. And then we got T of 30 days because this one 40 days and the first one is 10 days. So 40 minus 10 equal to 30 days. And we can know the alpha or the coefficient by using this equation. 50 equals to 100 times e power minus alpha times t, where the t is equal to 30 days. And after that, we got the alpha of 0.023. So we can use the deflation curve equation of K equals to K0 times e power of minus 0.023 times t. This curve can be used to draw this base flow or deflation curve. How about if there's no rain in 120 days? So we have to calculate the surface runoff. From the data, we already know that after so many days without rain, the surface runoff will be decreasing. For example, here we have 10 days without rain, we have 100 surface runoff, but after 40 days, we only have like 50 meter cube per second. Of course, after 120 days, the surface runoff will be also decreasing. So we can calculate it using the deflation curve that we already obtained before to get the flow rate after 120 days of no rain. And we got this 7.96 meter cube per second of the flow or the surface runoff in the watershed. So the surface runoff become lesser and lesser so that it can like reach zero soon. After like so many days without rain, it can reach zero surface runoff. So it will be the river will be dry until there's rain again, and then the surface runoff will be increasing again. So what is the effect of watershed properties on the shape of hydrograph? So as I mentioned earlier, there are many types of hydrograph shape and the watershed properties. So the effect of these watershed properties on the shape of hydrograph. So the shape of hydrograph is strongly influenced by the intensity of the rain, the duration of the rain, and the condition of the watershed before rain occurs. It also influenced by the shape of the watershed. Here I have an example between the types of different shape of watershed and the effect of the hydrograph. You can see on the left side is the different watershed shape. The first one is the long shape, and then a little bit of triangular, and then the third one is a little bit of round, I guess, ellipse here. And for the hydrograph, we got different trend of hydrograph. As you can see, we have the ABC here. The B is you can see it reached the same Q, same discharge at different time. Like for the B is the first one to reach the peak discharge, and for the A is the longest one to reach the peak discharge. Like it needs more time to reach the same discharge with the watershed B and C. So which is same discharge reach at different time depending on the watershed shape. How can that happen? So here we have the different watershed shape, and as you can see, the water is flowing from the upstream to downstream. So for this upstream, the upstream is the upper level of the river. The downstream is the outlet. So here we have if the discharge from the upstream reaching downstream at the particular time, which means it reached the peak of the discharge. So here we have the watershed of B reaching the peak of the discharge first, because it has the shortest distance between the upstream to downstream. As you can see, the distance is quite short compared to the watershed A and watershed C. And then the second one, we got the watershed C to reach the peak discharge. And the last one, we got the watershed A, which has the longest distance between the upstream and the downstream. So yeah, that's the effect of the watershed properties on the shape of hydrograph. So the duration which the water flows will be affecting the hydrograph. And here we also have A1 and A2. For example, the watershed area, which has different shape but the same area, and the rain, which has the same intensity, falls in the area. Its resulting flow in the observation points, A, B, C, will also have different shape of hydrograph. So even though the rain intensity is the same, the area is the same, but because of the longest distance between upstream and downstream, it will cause the differences in the shape of hydrograph. Here, for example, in area A, if the rain falls in the area A from point A to the upstream direction, the resulting point is the curve A1. If the rain moves from upstream to downstream, you will get the curve A2. Which means if the rain falls in the area A from point A to the upstream direction, the resulting flow will be like the A1. So if the water flowing from this outlet to the upstream, the curve will be the A1. And for the if the rain moves from upstream to downstream, from the upstream to downstream to the outlet, you will get the curve A2. The differences here is the discharge. The discharge will be increasing slowly if the water flowing from the area of A, from point A, the upstream direction. But if the rain moves from upstream to downstream, you will get the curve A, which discharge will be increasing in the time near the end of the hydrograph. So here we have the triangular hydrograph, which previously we addressed as a single peak hydrograph. So if you got the hydrograph problem, which is not stated what is the shape of the hydrograph, you can always assume that this the hydrograph is a triangular hydrograph. Here we have the TR, TB, and TC. And the TR is the duration of the effective rain. The TC is the time to reach the peak. Time needed to reach the peak discharge. And the TB is the flow duration due to rainfall effective rainfall. And using this triangular hydrograph, usually in the problems, the hydrograph is not known, but the TC, TB, and TR is known. So for example, you got TC of like 2 hours, and then you got TB of 4 hours. Oh, from that you can already make a conclusion. Oh, it should be triangular hydrograph. It will be different if there is the different TR. Like it can be like a trapezium hydrograph, but in this case, it's not like that. So for TC, time to reach the peak discharge can be like this if the rainfall duration is smaller or equal to the time to reach peak discharge. I think it will be clearer if we use the example. Okay, first, if you have like the surface runoff, here we have the surface runoff, and here is the hydrograph. The curve will be similar with triangular hydrograph. The differences will be only for the triangular hydrograph, the shape will be triangular, so that you will calculate the area of this hydrograph easier using the triangular equation. Area of this triangle equal to the volume of the flow. So if you have like this triangular, you can calculate the volume of the flow by calculating the area of the triangle. Here we have like this, when the time of the rain equal to the time of the peak, which means the rainfall occurs the same with the time needed to reach the peak discharge. So that after reaching the peak discharge, the rain already stopped, so there's no more addition to the hydrograph. So the shape will be like this, will be triangular like this. To calculate it, First, you need to calculate the effective of the rainfall equal to the volume of the flow divided by the watershed area, or equal to the alpha times rainfall total. This one is already mentioned in the previous lecture regarding the precipitation. And there's also volume of the flow equal to half times QP times PP. As you already familiar with this equation, this is the equation of the area of the triangle. Half times the peak of the discharge times the time days. And you can also calculate the effective rainfall using alpha times the intensity of the rain times the time of the rainfall. And then from this, R effective equal to this R effective. So we use the equation of volume of flow divided by watershed area equals to the R effective, this one. And then from that we can calculate the peak of the discharge equal to 2 times alpha times rainfall intensity times watershed area times the time of the rainfall divided by time days. How about if the time of the rainfall equal to the time of the concentration? Time concentration is the time needed to reach the peak discharge. So time concentration, you will also meet with this time concentration again in the drainage class. But this time concentration is the time needed for the water flowing from the origin, for example, from the upstream to reach the measurement point, for example, to reach the downstream. So the time of concentration, Tc, is equal to that, where the 2 Tb time days equal to 2 times time concentration. Usually it's like that in the triangular hydrograph. When the Tc is equal to Tr, Tb is equal to 2 times Tc. So after that, we can calculate the QP peak discharge using the previous equation, but changing the Tr and Tb with the Tc. And after that, we can get this rational formula. QP equal to alpha times rain intensity times the area of the watershed. Yeah, and to get the matrix unit of this formula, if you use the matrix unit, you can change it into QP equal to 1 divided by 3.6 times alpha times intensity of the rainfall times the area of the watershed, where the QP is equal to meter cube per second, I equal to millimeter per hour, and the kilometer square for the area of the watershed. Yeah, it is converted from this complicated number into the 1 divided by 3.6 because because of its discharge units in meter cube per second, but the rainfall intensity is millimeter per hour, so we need to convert it. Yeah, this is an important formula this rational formula because you will need to use it again and again and again in the next lectures. Like if you use it, you will use it for drainage. You will also use it for calculating other peak discharge in an hydrograph. So it will be useful if you remember this rational formula. How about if the TR is more than TC? So first, we got the TR equal to TC. So TR is the time of the rainfall. TC is the time of concentration, time needed for the water flowing to the furthest point of the watershed upstream until it reaches downstream. What if the TR is more than TC? So this case is when the water flowing from the upstream reaching downstream, but the rainfall is still happening. What happens? So this type of the hydrograph will happen. Like if it's already reached the peak, but there is still discharge added into the discharge. So the discharge will be like constant in a few time steps. After the rainfall stops, it will decrease. So if the rainfall is happening longer than the time concentration, the hydrograph will not be like the triangular hydrograph, but it will be like a trapezium hydrograph. Trapezium, yeah, trapezium hydrograph. So the equation will also be different because if we calculate the flow volume, we need to calculate the area of the hydrograph. So that for the previous equation, we use the equation for triangle, like the area of triangle. But here we need to use the equation for the area of the trapezium. Here we got the effective rainfall of alpha times the rainfall intensity times the time of the rain, TR. And then we can calculate the flow volume based on the equation of the trapezium here. And then using the same matrix units, the discharge can also be calculated using the same equation. Like the peak discharge will be calculated using the same equation or the rational equation. The difference is only when you calculate the flow volume, you need to know the shape of the hydrograph. Is it triangular with the same side, or is it trapezium, or is it triangular with different length of each side? And the third one, the last one, if the time of the rainfall is less than time concentration, and time base is equal to 2.67 of time of concentration. So here, actually, this is only an example. If you encounter a problem, there are a lot of different types of the problems that can occur with this example. Like it can be like TB, time base, equal to 3 times TC. Can be it can happen also. So it depends on the problems that that happen at that, for example, in the exam or in the exercise. It's not always like this, but yeah, the number can be different, but the way to solve it will be the same. If the TR less than TC, which means the rainfall stops before the water from the upstream reaching downstream. What happened? This will happen. So the differences is for this problem, you need to calculate the flow volume using the equation different than before, like because it's not the same side of the triangular, because it has different length. Like after TC, the length is longer because of TB equals to 2.67 TC. But here you can see there is this particular TC. How do we know the TC is right there? TC is when the key P is happening. So we need to see, or we need to calculate the key P first, so that we can draw the hydrograph. And for the TR, here we have like time lag. Time lag is the time between half of the TR until the TC. So there is this time lag between half of the rainfall until it reaches time of concentration. And this L, the time lag, will be useful in calculating the peak discharge, because we didn't use it before in the previous example because of the TR equal to TC. But if the TR is less than TC, we need to use the time lag. Time lag is the time differences between half of the TR, or half of the time of the rainfall, and the time of the concentration. And then after that, we can calculate the GP using this rational equation. Yeah, for today's class for surface runoff, the material is already finished, but there is still like an example. As you already know, we only talk about the theoretical things. There are still like an example of the question that you can solve using this this thing that we learned today. I think I will talk about it later in our next meeting on Thursday. Or maybe if you have any question, we still have a little bit time left. So yeah. Is there any question?
Excuse me, ma'am, I have question.
Yeah.
From the triangular